All right, I'm going to video this for Shayna. So, I just want to talk quickly about some of the stuff you did last night, okay? How are the textbook questions? Pretty easy. I'm going to scooch to my answer key, so look at your stuff now. And then everything that you did last night, you have to leave on your desk for me. I eventually will get to it. So, for the pure covalent, which is just nonpolar covalent overall, polar covalent, and ionic, you guys can, I mean, all these answers are in the back of the book, but I just, if you happen to not look in the back of the book, excuse me, or you happen not, you weren't able to understand what was the answer in the back of the book, it's the same electronegativity, it's going to be definitely nonpolar covalent. There's a slight difference, obviously you can't always have the numbers that are known, but if it's carbon and anything that's fairly electronegative, it's going to be polar covalent, which is going to have a dipole moment. The carbon and sulfur, they're really close to each other. They're that diagonal rule. No, not allied, no. They're fairly close to each other in terms of electronegativity, so that one's actually nonpolar covalent, but you could look at the Pauling list if you really want to get down and dirty with it. And then the strontium and oxygen, two totally different things, ionic because you've got a metal and non-metal. We all okay with the strength of the carbon bonds? Yeah, so this one's if it gave you it was a HCCH, I think was how it was written actually. They try in the formula to show you how they're connected. So don't get crazy and be like, no, I think I want to put this H or this H. No, try to go in the order in which they have written it for you. And so the formula was essentially the same. You just added H's. As you add H's, you have to add ligands and bonds to the side, which consumes your electrons. So this one had a triple, this one had a double, this one had a single bond. So remember your organic, ethane, ethene, ethine. Totally. Yeah, we would never forget that. Okay, so then the strength is going to be, the strongest is the triple bond, which was the strength increasing strength goes from the single bond to the double bonded one to the triple bonded one. I just numbered them. And then the length is directly the same because as you have a long bond, it's less strong. Shorter bond is medium strong, and the short bond is super strong because the nuclei are attracting each other's electrons clouds very effectively. And then I think what was this, formal charge? Oh yeah, which of these is the best in terms of formal charge? Always our best case scenario is zero formal charge, especially if you have a zero net charge on whatever the heck we're doing. But sometimes, like I think Jordan and I were talking yesterday about sulfur trioxide, I think it required, I think it was two double bonds, not three double bonds, because the double bonds have some issues with their stability. They have to have places to overlap, which we're going to see today with vaporization. So it'll make a lot more sense today. And then geometries. We have to really just hammer those geometries because I know we have a lot of practice with this, but you have to be able to look at something, almost draw it in your head sometimes, and then figure out the molecular geometry of molecules. Like for some multiple choices, please draw those dangly structures, right? But you may not have time for everything, so you're going to kind of get good on both ends of the stick. Okay, so this one was, they had a lone pair on the phosphorus, so electron group geometry is really easy. What are the 5 electron group geometries? Linear? Tetrahedral. There's one between those. Trigonal planar, that's if you have 3. That's only going to occur, bless you, that's only going to occur with anything with just boron, right? Because boron's pretty much the only one that's going to form be happy with 6 valence electrons. All right, so what's that called? Linear, trigonal planar, tetrahedral, trigonal bipyramidal, that's when you have 5 electron domains. 6 electron domains? Octahedral. So electron group geometry is really easy. Just count them up and go, yeah, straight 3s, 4s, 5s, or 6s, right? And then the molecular geometry, those, when you actually take into consideration how are these electron lone pairs squishing and pushing and repelling the other parts of the atom. Then you say, okay, what's the shape look like after the repelling has occurred? Which in this case, after that lone pair pushes, they're going to push those 3 legs to the side. My head's a lone pair, okay? Push them to the side, you have like a pyramid appearance. So that's after the fact. And then the bond angles are going to be approximate because it's really dependent upon what the ligands are. So this one asks for like which ones deviate from the general bond angle. And since these guys have, those fluorines, those ligands have 3 huge lone pairs around them, they can only get so close because then they're going to start to repel, right? So they also can't be too close to the lone pair. So that's why I just said it deviates because of the lone pair. That's pretty much the explanation for anything with lone pairs. So, how's that one? Good? How about the rest of them? Anything I need to go over? Yeah.
Why is that bent and not linear?
Because there's only one shape that 4 electron domains can take. What is it? 4 electron domains. Nope. 4 electron domains. Shape. Tetrahedral, right? If I take off 2 of these ligands, it's never gonna be straight, ever, because the ligands are at 90, 109.5 degrees from each other. So it doesn't matter which ones I take off. There's never a way in which that's gonna be straight. Never. It's always gonna be bent because the lone pairs like to be far away from each other as possible. But hey, that's a good segue to the video I didn't show yesterday, but I want to show today. So thank you, Abby. Let's watch the video. All right. Pandora's off. Yay. All right, this is a really good video. So, I don't show videos a lot, but let's watch this.
What is the shape of a molecule? Well, a molecule is mostly empty space. Almost all of its mass is concentrated in the extremely dense nuclei of its atoms. And its electrons, which determine how the atoms are bonded to each other, are more like clouds of negative charge than individual discrete particles. So a molecule doesn't have a shape in the same way that, for example, a statue has a shape. But for every molecule, there's at least one way to arrange the nuclei and electrons so as to maximize the attraction of opposite charges and minimize the repulsion of like charges. Now let's assume that the only electrons that matter to a molecule's shape are the outermost ones from each participating atom. And let's also assume that the electron clouds in between atoms, in other words, a molecule's bonds, are shaped kind of like sausages. Remember that nuclei are positively charged and electrons are negatively charged. And if all of a molecule's nuclei were bunched up together, or all of its electrons were bunched up together, they would just repel each other and fly apart, and that doesn't help anyone. In 1776, Alessandro Volta, decades before he would eventually invent batteries, discovered methane. Now, the chemical formula of methane is CH4. And this formula tells us that every molecule of methane is made up of 1 carbon and 4 hydrogen atoms. But it doesn't tell us what's bonded to what, or how the atoms are arranged in 3D space. From their electronic configurations, we know that carbon can bond with up to 4 other atoms, and that each hydrogen can only bond with 1 other atom. So, we can guess that the carbon should be the central atom, bonded to all the hydrogens. Now, each bond represents the sharing of 2 electrons, and we draw each shared pair of electrons as a line. So now we have a flat representation of this molecule. But how would it look in 3 dimensions? We can reasonably say that because each of these bonds is a region of negative electric charge, and like charges repel each other, the most favorable configuration of atoms would maximize the distance between bonds. And to get all the bonds as far away from each other as possible, the optimal shape is this. This is called a tetrahedron. Now, depending on the different atoms involved, you can actually get lots of different shapes. Ammonia, or NH3, is shaped like a pyramid. Carbon dioxide, or CO2, is a straight line. Water, H2O, is bent like your elbow would be bent. And chlorine trifluoride, or ClF3, is shaped like the letter T. Remember that what we've been doing here is expanding on our model of atoms and electrons to build up to 3D shapes. We'd have to do experiments to figure out if these molecules actually do have the shapes we predict. Spoiler alert, most of them do, but some of them don't. Now, shapes get more complicated as you increase the number of atoms. All the examples we just talked about had one obviously central atom, but most molecules, from relatively small pharmaceuticals all the way up to long polymers like DNA or proteins, don't. The key thing to remember is that bonded atoms will arrange themselves to maximize the attraction between opposite charges and minimize the repulsion between like charges. Some molecules even have 2 or more stable arrangements of atoms, and we can actually get really cool chemistry from the switches between those configurations. Even when the...
What just happened? You saw the photon came in, energized the thing, and what happened? You see that? No? Here, let me show you again. Because you've got to kind of watch fast here. Photon comes in.
Really cool chemistry from the switches between those configurations. Even when the composite...
So what is that called when it's the same formula, different arrangement? Huh? Oh, isomers, because the resonance is different places of the bonded pairs, not really different places of the atoms, because the atoms are exactly the same place in that resonance structure. Those are isomers. what kind of isomers just happened if you went from here to here? Cis and trans, right? So it's really huge and long, but then you can see at the end, it went from, I don't know which carbon it actually turned at, but it went from cis to trans geometric shape, okay? And that's just because the photon energized this double bond and it switched.
The position of that molecule, that's to say the number and identity of its atoms, has not changed at all.
Okay, so I really like the video because I don't do it justice when I'm trying to draw those 3D images to show you the repulsiveness of it, but you can see it just really just rotates in space. One thing that you probably didn't notice is that double bonds, they don't just like fling themselves around and really rotate a whole lot like a motor, okay? They can't do that very well because double bonds are locked. And I'll tell you why today. So I'm actually going to introduce a little bit of hybridization today. You guys will do a simulation, and then we'll finish up. But I have some things I need to touch on that I didn't do like the Friday video yesterday's. So I just want to touch on a couple things today, like vocabulary and then melting point, okay? So read the right there. Give me an example of a molecule that has delocalized electrons. Delocalized electrons, like benzene does. Define what delocalized based off this statement. What do you think delocalized means? It's pretty simple. That's what it means. It's not like where you think they're going to be. What does localized mean? Well, localized means like you're in a location. You are here. Like you were localized in my room right now. If you're delocalized, you're in another room. So I like the, it's not where you thought they were going to be, but it's basically they can be here or they can be here, or they can be here or they can be here. Delocalized means not in one specific location. So benzene, looks like this, or does it? Does it look like that? What's the cheap way of doing this? The circle to say, hey, those double bonds can be any of these places, except, it's every other one. So that's just meaning that those electrons don't have to be here. They could have been here, here, or here. So it's just delocalized. It's not localized. Sometimes double bonds and triples are localized. They're literally in that place. You cannot change them. So just making sure, I want you to know that delocalized means multiple locations. Okay, can be in multiple locales. Okay, just that's what a resonance structure is actually representing, different locations of the double bond. And then that's all I want to tell you there. And then I have something with melting points on the next slide. Just kind of like finishing up the little things I need to tell you. Give a thumbs up if you good. Just fast. And then just did that. Okay, so saw the video. Sorry, I may not do melting points for a second. Why do we care about polar structures? We care about if they have the ability to react to a magnetic field. Okay, that's the only reason we care about polar structures and being able to draw them with polar dipole moments, and then overall saying they're polar. And we're going to practice that when we get to intermolecular forces Thursday. So we're going to practice with polarity a lot more. So kind of keep that on the back burner for now. But you can see definitely this is water. This is carbon tetrachloride. Water has a dipole moment pointing upward, like over the whole entire molecule. Then it's in very, very polar, meaning this is partially negative up here, and this is partially positive down here. So it will react to a magnetic field. And actually, you can take a burette and you hold up something that's magnetized or static electricity, and it'll bend the field of water. Another way that's totally not chemistry, but it's, what is chemistry? Have you seen it? I don't know if they have it at the Discovery Place anymore. They have this water, stream of water, and they run a different frequency through it, just like a sound frequency, and then it will take on the motion of the wave. Like whatever size wave, gamma rays really small versus, radio waves are really long, and then give it a different frequency, and it like spins a different way, and then it makes like these weird shapes in the waves, and it's just like running through air. I will find a video for you. It's awesome. I don't have the equipment for that. I have an amplifier, and I do have a frequency generator, but I don't know how well this works. Somebody used it in honors chem. I can't remember who used it, because I got it from UNCC, and then they didn't want it back. I was like, sure, I'll keep it. Don't know one else who used it, I'll use it. But anyway, carbon tetrachloride doesn't respond because it's nonpolar all the way. Okay, melting points. So this is based on your knowledge of bonding and polarity. Bonding comes in three varieties. What are the three? For now, anyway. Covalent, ionic, and metallic. Okay, so actually before I show you here, you have your sheet, you have a, pull out your packet, pull out like a highlighter. I was gonna review this because I told you guys to read this, but then I just wanted to highlight the specifics, so I literally highlighted the specifics here. Anybody need a highlighter? Highlighters. Hey, pass out. I mean, pass those out. Don't pass out, Jordan. Don't pass out. I have more highlighters. Does anyone else have a highlighter? Here's another one. Going once. Nice try, Grace. Here's a green one. Green one. Anybody? Green is not for losers. I'm gonna hit Hansel on the head, so wait. That's pretty good. Okay. So, or underline, I don't care. So I just wanted to highlight the things that I feel like are most important, because this next unit we're doing after bonding, we are really digging deep into solids and liquids, and obviously these can all because they're solids. So positive ions and electron sea. Okay, that is literally how it is explained. This is a sea of electrons that have been just, cast away, and the positive charge remains in the middle. And so then underneath metallic again, you've got core of positively charged nuclei surrounded by a sea of, they actually didn't write this here, but a sea of delocalized electrons. So what does delocalized mean yet again? Multiple areas, not in one place, or multiple areas. So the sea of delocalized electrons looks like, here's a positive core, here's a positive core, here's a positive core, here's a positive core, electrons. And I'm going to just draw those negative signs here. They're just hanging out everywhere, okay? So they are obviously still attracted to the positive cores. That's why they don't just go bye-bye. They don't just go fly off the metal. Actually, they do sometimes. We've heard of the photoelectric effect. The light waves deliver energy to metals, specifically metals. And so, like, if a light wave, like purple violet light, okay, really, really energetic, hits this, it'll pop an electron off. And that's how solar cells work. Did I already tell you this? Okay, because I told Honors Chem, I can't remember if I told you guys. Okay, but that's just how free electrons can travel electricity. The sun does that because it's got all kinds of wavelengths of light. So it's how solar cells work. All right, so over here on the properties, things you absolutely have to know, which we are going to go into more detail, but I want you to know them anyway. Hard but malleable. Malleable means you can mallet it into a sheet. Yeah, so a flat sheet. High melting points and high boiling points, and that's because these positive cores are attracted like everywhere by the different electrons that are free to move about. Electrons are said to be delocalized, okay, but those delocalized mean that they're in multiple locations. They can still move. That means that they can conduct electricity and heat because the electrons are passing around the electrical conduction. Hey, you can pop right there on the desk. Thanks, Khalil. Malleability and ductility. Ductility means what? Pulls into a wire very well, and that's obviously why we make wires out of metal. Right? It's very important. And then the last bit here, why in the heck is the melting point of all these metals, why are they so high? That little tidbit down there is going to give you comparative melting point. So they're high because their electrons, the delocalized electrons, are attracted to their metal cores, but why is magnesium's higher than sodium's, for example? They have doubly the charge of the metallic cores, and so that's just Coulomb's law in action again. The positive charge of the core, higher positive charges yields higher strength. Okay, so then we got ionic, so definitely transition of electrons. Electrostatic force is always a good word to use with ionic compounds. And then crystalline lattice. The crystalline lattice just shows you that it's a hard solid, but it's a very organized solid. It's not just a bunch of crap put together. It's in a nice, layered lattice structure. Like if you pour a bunch of golf balls into a tub, they're going to line up in the dimples of each other. That's how one of the examples that was used. If you have softballs, they're going to do the same thing. Tennis balls are going to do the same thing. They form a lattice. Okay. Over here, hard and brittle. Brittle means the fact that if I take my huge salt crystal and I threw it on the ground, what would happen? It would shatter, but it would still have its cubic shape. Okay, because what happens is it shatters on these fracture lines, and it just fractures along the crystalline lattice. But it's brittle because I can actually force that to happen. And how do you think you get a salt lick, deer salt lick? You know what I'm talking about? Whose country here? Nobody? Okay, thank you. So it's just a big, huge salt block you put out for deer to lick, so you can then have them in different parts of life. Yeah. So there's
animals.
or you take them for pets, okay? You can take them.
take them for pets.
So take them for a walk. That would be great. Or you can put them in a salt shaker, right? So you don't have just huge lots of salt out there. Non-conductive is a solid because the electrons are locked in place. That was on your midterm? No, was that on your electrochem test? Like why was aluminum oxide conductive as a liquid but not solid? I think that was on your electrochem test. I know I remember that, so I'm not making this up. Okay, but it's non-conductive as a solid because the electrons can't outmove. They definitely are conductive as molten state though, or aqueous state. High melting point, Coulomb's law. Because they have true positives and negatives, which are definitely electrostatically connected. I'm not doing that work yet. We're doing that next unit. I'm not doing all the covalent molecular ones yet, but I just want to show the direct contrast. You've got melting points that are much slower, boiling points that are much slower, due to their polarity. I mean, it's really is just due to their polarity. So if something is polar, they do have stronger attractions from one another. But you can still melt them and heat them up and boil them at reasonably low temperatures. If something is nonpolar, there's absolutely no magnetic attraction, not absolutely, asterisk there, somewhat no magnetic attraction to each other, so then you can pretty much separate them at any given time. Now, during boiling and melting, what is actually separated? What's actually broken? Huh? Be careful with your answers here. If you boil or melt something, what's actually being separated? Take water, for example. The what?
Individual molecule.
Like that?
Like,
What's the two molecules are separated, or this?
like the two molecules separated, not the bonds within the.
Okay. So the intermolecular forces between molecule 1 and molecule 2 of water, this lone pair that's attracted to that's attraction. That attraction is called a what? Hydrogen bond. Hydrogen bonds are fat lies, right? They're not bonds at all. They're just attractions. I don't know why we call them hydrogen bonds, but it's just a lie. It's not a bond. It's an attraction. So that attraction is overcome by heat, and those two particles go separate directions, which make them seem as if they're facing because they are, right? The bonds themselves, the OH bond here and here, aren't touched. Those are called interparticle bonds, and these are called intermolecular forces. Interparticle means within the particle. Intra, between. We're going to talk about that. Okie dokie. Let's do no more of this. No more of this. Okay. Now, melting points. Of this, I know I'm everywhere today. Consider the following substances and their melting point and explain these relative values of melting points of these substances. Which one's the highest? Strontium sulfide? Why? It's ionic. Okay, so it's ionic, which makes it higher. Why? I heard something with charges. Give me one. Bigger charges for the Coulomb's law thing. Okay, so larger charges will yield larger attraction, and forces of attraction yield stronger bonds. Okay, so I like ionic, the fact that they have pure charges, like we got a 2+ charge and a 2- charge here, so that's actually quite a large charge magnitude charge product. Okay, so why is this one smaller? Why is potassium chloride smaller? So lower charge product, okay. Sorry, -1. Okay, so why is water next? All of these are covalent. Okay, it's not only polar, it also has the strongest intermolecular forces. So it's really polar, and it's got strong hydrogen bonds holding it together. We're going to get into more of that, the polar part and the HB, hydrogen bonds. And then the rest of these, what's that shape it takes? Hydrosulfuric acid, what's that shape? Bent, because it's got two lone pairs, just like water does, right? But why do you think it's got a lower melting point than water? Because it's definitely polar, because water's polar, it's got the two lone pairs up here, so it's definitely polar, but why is it different? No hydrogen bonds, it's got just plain old dipole-dipole, or maybe it's, no, I'd say it's dipole-dipole. This one methane, tetrahedral shape, polar, non-polar, non-polar, because all the bonds of opposite are blah 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 blah. I can't talk today. The dipole moments cancel each other out in the tetrahedral arrangement, so it's going to be non-polar molecule, and so it's only actually undergoing London dispersion forces, which is the weakest type of IMFs, intermolecular forces, meaning you can melt it pretty easily. So, I mean, negative 120 or 82, that's really low, really, really low. Okay, so we're going to start prioritizing things based on intermolecular forces and interparticle attractions. Okay, I'm going to introduce you to hybridization now. Yay, and I didn't blow up any balloons because I just can't handle balloons. I just can't. My lung capacity. Can't handle it. Okay. Oh, before we get there, tell me some things that you saw from your reading. Just shout out anything that stuck out to you. Or that was really confusing to you. What you gotta do? Alright, so sigma and pi bonds. Sigma just means single bond. And then pi bonds means either a double or a triple bond, okay? Right, so like, you know, if you give me methane, I'll just do that example that we had in our notes here. I'm going to do a little bit here. H, C, H. If I have H's here, this C to C bond is just a single bond, which is a sigma bond. But if by chance I was able to make this ethene, I would have a sigma plus a pi bond to make a double bond. And if I was able to go further and go ethyne, I mean a triple bond, I got a sigma plus a pi plus a pi. That's all that is. I can do more of that though, don't worry about that yet. Anything else that stuck out to you? Grace.
Homo and heteronuclear diatomic.
Okay, so homo and heteronuclear, we're going to get that with molecular orbitals. That's like the last thing we'll do. So let's wait on that one, okay? What else? What from the beginning part? What is hybridization? Like, what does that mess? Okay, so it's an intermediate orbital. They overlap them to show that the bond exists there, because if electrons are shared, they have to be shared in the locations in which they live. Where do electrons live? Orbitals. You got to take two orbitals and overlap them so you can have a covalent bond. So I've actually tried to a diagram of this here. This is a hybridization orbital. This is what it looks like. It looks like a big sausage, like it's still in the video. That's what reminded me to draw it here for you. It's literally, this is methane, okay? I've got carbon with 4 bonds, and then the electrons are little pink things. They're spinning in opposite directions. They're shared, 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 shared. That looks the same as carbon with 4 bonds bonded to hydrogen, right? But these have a different shape than the s, p, d, and f shapes, okay? Because they're a blend of different orbitals. What does the s shape look like? Orbital. Circle. What does the p shape look like? D? Okay, and that's as far as I'm going because I can't draw an F, okay? That's it. So if I take these two together, what happens is it blends the shape, and it looks like this. I'm going to draw it sideways, okay? That's what it looks like. I can draw another one. That one's on the this axis, x-axis. We got another one on the y-axis, and then we got one on the z-axis. All right, why did I draw 3 of them? There's 3 different p orbital orientations. So I took an S and I blended it with the px, py, and pz, and it looks like that. It's just Play-Doh mushed together, people. That's it. But the only reason we have to have a separate model is because there's exceptions to the VSEPR theory that we've already, got under our belt and we feel good about. But there's exceptions to that. We have to identify that. We have to recognize the chemistry behind it. The chemistry behind it, a little bit more wordy, and I'm going to get to that, but not all of that today. So, talk to me a little bit more about this. What else? What did you see that was different? I heard pi and sigma bonds, but we've got some letters that they were throwing at you. What were some of the letters? Really, so kind of what I've just drawn. Sophie, give me something.
Here, SP.
Okay, where are they getting these letters? What does it look as if they're putting together? Different orbitals of these different, where the electrons exist, the electron orbitals. So here they put together an S and 1 P. So they put together one s and one p. So one s and one p makes 2 orbitals. Hey, if you put two orbitals together, you get 2 orbitals. You don't make a million orbitals. That would be awesome. But we can't. We put 2 together, we make 2. But we put together 2 specific orbitals, and we make 2 blended or hybridized orbitals. And that's how you got 2 sp orbitals. But what else was not involved in hybridization? What still was left? We only used one s and one p orbital. What's left? We got d orbitals. Let's not skip what's in the middle though. We only used one s, which there's only one s orbital, right? The other 2 orientations of the p, right? So you only took this here. Let me actually draw those 2 p's here for you. So I'm gonna draw some green. We got this orbital and then this orbital. Okay, so we got SPPP. Okay, we took these 2, smushed them together, and we made these 2 hybridized orbitals. They just look funny. It's okay. We like them anyway. So we got these 2 left. So guess what? We have 2 sp hybridized orbitals plus 2. I'm just gonna say plus p because I don't want you to. That 2 doesn't matter. Plus another p orbital plus another p orbital that are not hybridized. They're just in normal shape. You know, they look normal. That's really important though because they are used in the really complex bonds that overlap each other above and below the atom. Those are the pi orbitals. Those are the pi bonds. So we're going to talk about this. But the most simple one that we have to talk about are the tetrahedral ones. Tetrahedral are going to be how many bonds are here? How many orbitals are used from carbon to bond? How many orbitals from carbon? What's the electron configuration for carbon?
1s2.
Okay, so of all the electrons that it has, which ones are used to bond? AKA they're valence electrons, right? The valence electrons are used to bond. This one's already full. It's full to its little S2S octet or duet rule, right? So we got 2s2 and 2p2 to work with. We got 2s2 and 2p2 electrons to work with. We have 4 electrons to work with in a bond. We got 4 bonds. Carbon usually likes to form 4 bonds because it's got space for it, right? It's got space to make octet. It's got to get up to 8 in its valence shell. Currently it has 4. It needs 4 more. It has to share those 4 bonds with somebody else. Hydrogen, for example, because 4 hydrogens will give away share 4 valence electrons. So what happens here is we have to recognize that we have an s orbital and we have 2 p orbitals to work with. We have this empty one over here. That's the 3rd p orbital. We don't have any electrons in it. Can we put an electron there? Totally. It's called electron promotion. We can do that. We can't do it. Carbon can do it, right? So carbon can put its extra electron there, getting rid of one of them here. So what we can do is we go, oh, hey, I just need 4 different atoms to share, and we can all be happy together, right? But what we have seen in the lab is that this orbital should be totally different than these 3 because this is a small s little tiny orbital, and these are 2 big, huge, long dumbbell orbitals. So what you would think is that you're like, oh, I got 2 different looks to the bonds, 2 different energies to the bonds, 2 different shapes to the bonds because I've got 2 totally different shapes I'm working with. But what they found is that no, it's a lie. They're not different. They're all equally the same, which is why I've drawn them all equally the same. Well, the only reason behind, or the only explanation as to why they're the same is that we have changed the shape of the orbitals. When I say change the shape of the orbitals, I say hybridized. We have hybridized these 3 orbitals so that they all are the same length, all the same energy, all look the same on a diagram. So what we've actually done is we've hybridized them together, smushed them together as S plus P plus P plus P. Those 4 orbitals smushed together are called sp3 orbitals. Because how many S's do we have? How many P's do we have? 3. That's literally hybridization, okay? We'll do a lot more with this, but I wanted to give you that introduction because when you do the simulation, you need a little bit of background, okay? So, but how many orbitals did I smush together? Up here. I smushed together 4, so how many hybridized orbitals did I form? 4 again. Because I can't eliminate orbitals because I got electrons to hold. I can't just take them away. They're still there. but I've just made them look different. So I took 4 unhybridized orbitals, and I made 4 sp3 hybridized orbitals. It's just we call them something new now. Yeah.
On the drawing, what is the little raindrop?
That's what that thing is.
Oh,
That little tail.
those, like, numbers you see.
Yeah, it's like you have to draw them opposite of each other. I usually erase them in the end because they just look like retarded. So that's it. All right, so they exist there together. I'm going to show you one more of a double bond because we did go through one of those examples. Let's do ethene. So ethene, carbon still is our central atom, okay? Ethene looks like this. All right, so how many electron domain? Oh, hold on, before I get there. How many electron domains are in this methane right here? 4 electron domains. How many hybridized orbitals did I form? 4. The numbers all match. If you have 4 electron domains, you need 4 hybridized orbitals. How many electron domains are around this carbon here? Electron domains are just locations in which electrons exist. One exists here, one exists here, one exists here. They just happen to have more electrons in that place. There's still only 3 electron domains there because it's an area in which electrons exist, not how many there are. So there's only 3 electron domains on this carbon and on that one, right? So how many hybridized orbitals will I need to make this work? Just this carbon, focus on one. Just 3. So I can't make 4 sp3 orbitals. I have to make 3 sp2 orbitals, hybridized orbitals. Now, how did I make those 3 sp2 hybridized orbitals? I took s plus p plus p. What's up with the next one? Like, where's the next p at? It's free. It's not hybridized. It's just chilling the same way it's always looked. So I took these 3 unhybridized orbitals, and I made these 3 hybridized orbitals, which has that funky looking little raindrop shape, okay? But I also have a free p orbital that's just hanging out, and I can use it. Okay, so let's use it. So these look like, here's carbon. It's got 1 bond pointed that way, 1 bond pointed that way for these 2 hydrogens. And I'm going to erase those because they, again, look stupid. And there's another one pointed toward that carbon because it has to have a shared space with that carbon. There you go. All right, so there's these 3 are the 3 sp2 hybridized orbitals. All right, carbon also has that extra p just there, and it looks like a p orbital. That looks like a p orbital. Okay, so that's it, just chilling, hanging out, okay? I need to move this though, because I need some space. I want you up here. Okay, well, that works. This one is sp2, and it's overlaying with a hydrogen atom, because that's what it says, hydrogen atom, right? How many electrons are they sharing? 2, because they got a single bond, right? It's 2 electrons, up, down. This one, how many are they sharing? 2. I'm trying to show them overlapping. I'm not doing a very good job, but they are overlapping, because that's all a bond is, just overlapping electron neighborhoods. That's it. And so this one is going to overlap with that carbon, though, right? So I can't show that very well, so I actually need to go and draw the second carbon. And I'm going to try to make this as least complicated as possible. So here's my second carbon. I got to give it a little space. It's sharing or overlapping with this one. A little raindrop thing. It's got another one this way and another one this way, because that's what we said. Hydrogen, hydrogen. You with me so far? Okay, love you all. This one has hydrogen hanging out, overlapping, hydrogen overlapping. How many electrons up here? 2 here? 2. Okay, we still have this one again is yet 3 electron domains. You got 3 sp2 hybridized orbitals. That's sp2, that's sp2, that's sp2, that's sp2, that's sp2, that's sp2, okay? All of these are sp2 hybridized. That's just the name that we call them. Then this one also has that extra p orbital that's hanging out. These exist, they're really tall, okay? I didn't draw them that tall, but they're really tall. These are much smaller. This shows the single bond between there. That's a sigma bond. That's just the single overlay of electrons because I didn't draw them. There are 2 electrons overlapping here. So how in the heck are we going to diagram this pi bond, this second bond that's existing? This space, intranuclear space, is taken. The only other space is above and below. And that's what happens. And this is all we have to draw. These overlap. Yeah? Like a little bridge. They overlap. And that's what a double bond is. A sigma, single bond, and then this is collectively 1 extra bond. The reason why that's collectively 1 extra bond is because there's an electron here and an electron here. So how many bonds total are in between? How many? Between? 1, 2, 3, 4. How many bonds are in between? I mean, electrons are in between here? 4. It's just we have to draw the double bond up and down. You can't just put them on top or just on bottom. You have to draw them up and down because they're big. Yeah.
So, for example, maybe a stupid question. Do I just draw 3 lines to show that?
You have to draw another p orbital and another p orbital in and out of the board. I'll do that tomorrow. And you don't have as many outside stuff. Doesn't that just look pretty, guys? You're going to be amazing at this. Yeah. Because each individual atom has its own orbitals. Each individual atom gets its own hybridized orbitals. So this hydrogen doesn't hybridize because it's got 1 electron. It doesn't have any other orbitals except for this, so it doesn't get hybridized. But if you have like carbon dioxide, for example, carbon would be sp hybridized and oxygen would be sp2 hybridized. Each of the oxygens would be sp2 hybridized. Each atom gets its own special hybridization. That's why I do 1 at a time.
You lost me when you drew a bunch of electrons jumping from orbitals.
They're not jumping, they're sharing space.
How though? Like, is that are the 2 extra p orbitals, are they like bending into each other?
Yes, and I can't draw that very well. But that's how you're supposed to draw it, okay? Hold on. Hold on. I'll show you a picture. It's a lovely picture. Those overlap, and it makes it look like a huge bubble. Okay, but I prefer this because I can't tell what that is. I can tell what this is. It's like pretty much these things go like this. And they have a whole electron there. And they have electron here. Okay, we are going to talk about this a lot more, okay? We have 30 minutes left. Let's try to get through some of the what's this thing called? Simulation. Unless you guys want to do the rest of the notes today, and we'll do all the simulation tomorrow. Vote. I know, I figured. Hybridization. Okay, let's just do